Reversible chemical reaction. Reversible chemical reaction occurs when the forward activation energy, that is from reactant to product, and the backward activation energy, that is when product goes to reactant, is comparable. When the two values are comparable, it means that the reaction could move forward and it could also move backward. Dynamic equilibrium. Dynamic equilibrium is attained in a reversible chemical reaction when the rate forward is equal to the rate backward, and therefore the concentrations of the reactants and products remain unchanged. It's imperative that in the exam that you mention that the rate of the forward reaction is equal to the rate of the backward reaction. It will not be correct if you just state that the concentration of reactants and product remain unchanged over time, because this can apply for an irreversible reaction where all the reactants has been converted to products. The Chatelier principle. The Chatelier principle states that whenever a closed system is being disturbed by a changing factor that disrupts equilibrium, like temperature, pressure, or concentration, the equilibrium will shift to annul or tend to annul the effect of the change. First, the word closed system cannot be omitted. Closed system means that it allows exchange of heat energy, but does not allow the exchange of physical matter. So let's take a look at the common factors that's typically asked. The common factors that typically asked is about temperature, pressure, volume of gas, and volume of water added. We'll take a look at each of the examples and discuss about it. Now let's take a look at this example and introduce changes to them. So the first change we introduce is to add more reactant. So for example, if we were to add more nitrogen, then based on the Chatelier principle, or in short LCP, the position of equilibrium will shift forward. If we decide to add more products by putting in more ammonia into the reacting vessels, then based on the Chatelier principle is to remove the product, so therefore the position of equilibrium would actually shift left. So in the exam, you can mention it's either shift left or shift backward. Next, if you decide to remove reactant, say we decide to remove hydrogen. If hydrogen is being removed, then the position of equilibrium will shift to favor less reactant. So in this case, the position of equilibrium will shift left or shift backward. Remove product. If the ammonia is being condensed, is being removed, then the position of equilibrium will shift to favor more products being produced. So therefore, the position of equilibrium will shift forward, or we can say that the position of equilibrium shift right, which will add catalyst, which will later explain, is that the decrease in activation energy for the forward reaction is equal to the backward reaction. So therefore, there is no change in position of equilibrium. Basically, by adding catalyst, you just split up the reaction forward and backward. Temperature change. When temperature increases, it favors endothermic. Since the enthalpy change of the reaction is exothermic, when the reaction is forward, means that when the temperature increases, the position of equilibrium will shift backward or towards the left. If we decide to decrease the volume of the reacting vessel, then it will favor fewer gaseous molecule. So on the left, there's actually 4 moles of gas molecule. On the right, there are 2 moles of gas molecule. So therefore, by favoring fewer gaseous molecule, the position of equilibrium will shift left. When we look at pressure change, we do not use pressure change as a way for us to determine the shift in the position of equilibrium, because at times it will fall short. Later, we have example to illustrate why. So when the pressure actually increases, we in fact can break down to a few possibilities. One, you actually add more gaseous reactant or product. You actually add more gas in the reacting vessel. Number 2, if the pressure increase, then there's a possibility that the volume of the reacting vessel actually decrease. Finally, temperature increase could also be due to the fact the temperature of the gas has increased. So let's take a look at another example as illustrated here. If we decide to add solid reactants or remove solid reactants or solid products, there will be no change in position of equilibrium. So it means in this case, if I were to add or remove this BiOCl, there will be no change in position of equilibrium. Later, when we get on to the next chapter, we'll explain why mathematically. Finally, if you want to look at the change in the total volume of water, so in this example itself, let us increase the volume of water by adding more water. In this case, if more water is added, it favors more aqueous ions or molecules. So the total volume of water in the reacting mixture is similar to the volume of a vessel when gaseous reactants are reacting. So in this reaction here, you have one aqueous molecule and a water molecule that will combine to give you 2 HCl molecules, but the HCl molecules are in fact hydrochloric acid, which will further break down to 2H plus and 2Cl minus, since it is actually a strong acid. So therefore, because of this, we can say that by adding more water, the position of equilibrium will shift forward or shift towards the right. The reason is because it favors more aqueous ions or molecules. Let's take a look at the percentage yield versus the pressure graph for the example that we covered earlier on the production of ammonia, and as well as the percentage yield of ammonia versus the temperature. So as the pressure increases, of course, in this case, the pressure could increase by making the volume of the reacting vessel smaller. So if the reacting vessel becomes smaller, then it will favors fewer gaseous molecule, which in this case, here got 4 moles of gaseous molecule on the left and 2 moles of gaseous molecule on the right. So to favor fewer gaseous molecule, the position of equilibrium will shift forward or shift right, which means you'll end up producing more ammonia. If I produce more ammonia, the percentage yield will increase, and hence the graph. In the case of temperature, as the temperature increases, increase in temperature favors endothermic reaction. And the enthalpy change for the reaction given is exothermic, and that is for the forward reaction. And therefore, increase in temperature, which favors endothermic, means that the position of equilibrium will shift backward or towards the left. And hence, the amount of ammonia will actually drop. And therefore, the graph for the percentage yield of ammonia is as such.